This is a neat one. I like this. Let's sketch the curve represented by the equations below by eliminating the parameter and adjusting the domain of the resulting rectangular equation. What? Okay. So we are going to, well, eliminate the parameter, and up until this point we've solved for t and plugged it into the other one. Solve for t, plug it into the other one, and had to deal with the domain appropriately. Yeah, okay, that's what we've been doing. Well, now things change just a little bit, and I want to show you how very difficult it would be to use that same process. Also, notice we're using theta and not t. We're dealing with trig here, so it's common sense to use theta. You don't have to, but if you want to. In a minute when we use the calculator, we won't. So if I were to solve for theta, which is the parameter, I would divide by 3, and then I would do an inverse cosine. Oops, it doesn't have an a in it. Well, it does if you call it arc cosine. And that gives me theta. I'm going to take that and plug it in here. Don't write this because it's going to be a sloppy mess. So 2 sine of arc cosine of x over 3, and then it is doable but highly awkward and weird and not fun. So let's not. Instead, let's do something that may not automatically pop in our minds. What we're going to do instead is solve for cosine right here. So cosine is, we'll just call it x over 3. And we're going to solve for sine over here. And if you're like, why would you do that? You'll see. Sometimes you just got to know where it's going to see where it's going. That made no sense. Okay, let's go old school for a second. Here's something I know about sine and cosine. Sine squared plus cosine squared equals 1. It's good to know, isn't it? Okay, I agree. So sine squared theta, my goodness, don't leave your variable out there. All right, sine squared theta plus cosine squared theta equals 1. And so I'm going to take y over 2. I'm going to square it, and I'm going to take cosine, which is x over 3. I'm going to square it, and I'm going to set it equal to 1. And now I have y squared over 4 plus x squared over 9, and that's equal to 1. This is an ellipse. Now, a lot of pre-calculus classes don't get into the depths of how to graph this and what it all looks like, but this is an ellipse that is centered at the origin, and it is basically like a flattened circle. Let's use the x values first. The square root of this number, which was 3, we saw it a second ago, that is how much we would move left and right to define the width of our ellipse. And the square root of this number, the square root of this denominator under the y, is going to be 2, of course, and that is how far we move up and down from the center. And this is our equation. And it creates a neat little ellipse. So, just for fun, let's graph it. And you'll see what I'm talking about here. It's a good way to graph ellipses, just in case you really want to graph ellipses on a graphing calculator. So we'll type 3 cosine t, they're using t here, and we'll put 2 sine t for this one, and we'll just go to a standard window. Just zoom standard. There it is. Isn't that neat? Ha, I like that. I like it very much. The next problem is asking us to sketch the graph of this parametric equation, and it is only asking us to sketch it, not to write the equation. Up here, they wanted us to write the equation and sketch. And to keep in mind, this was not a function, so we don't have to solve for y. We could have. We did in a previous example, and we did a plus or minus thing, but we're not. This is standard form of an ellipse. It is valid to write it like that. Okay, all we're going to do for this one is just graph it, and I've typed it in. And when I type it in, I am going to use t instead of theta, but it's the same idea. We did this on the previous problem. And let's just deal with some parameters here. Let's adjust our window, which I've actually already done. I am going to go for my parameter, which is t, or theta, from 0 to 12 pi. This is 12 pi. You could just type 12 pi, and it computes it automatically. This is a very valid t step. The x minimum is 0. The x maximum is also 12 pi. And the x scale, in case you wonder where that number came from, it's 2 pi. So if you type 2 pi, there it is. The y minimum is -1, the y maximum is 5. Okay, I'm going to press graph, and as I do, I get this. I've already graphed it actually before the video started. So we have that, and the point of this is so we can have a brief conversation that's going to seem a little odd out of context. But we're going to have a brief conversation about what a smooth curve is, and it won't make sense much until we get to the next lesson. But I think it's worth dealing with. Oh my goodness, that's an awkward hump. Now I know that what you see on the calculator is taller and definitely smoother because I'm having a hard time drawing them. because they went up. Mine was stretched out this way, and this one's kind of stretched out horizontally. But it's the same idea, and here's the deal. Smooth curve, smooth curve, smooth curve, smooth curve, bounce. Not a smooth curve. Smooth curve, smooth curve, it's a tongue twister. Bounce, and then lands. Okay, definition of a smooth curve. Very, very clunky until we understand how to take the derivative of x and the derivative of y in a parametric function, parametric equation set, and that's going to happen in the next lesson. But a curve represented by that in the interval is called smooth when those are both continuous on the interval and they're not simultaneously zero. So from what we see here, I'm going to go ahead and tell you the derivative of x and y is 0 here and here, technically here and here as well.